Thanks so much for inviting me. I'm gonna talk today about survival analysis for healthcare data. And many of you have probably heard of like models like the Cox proportional hazards model. I'm gonna rederive the principles behind that, and I'm gonna talk about how we can extend that into the deep learning kind of framework. Um, this talk will be more on the technical side, so I'm gonna assume you have some familiarity with probability theory. And I think it's best just to get into it. Please stop me if you have any questions at any time. Let's get started. Just a quick introduction. I'm an AI scientist. I used to work at Microsoft and I did my PhD at Cambridge. You can find out more about me on my website. Today's talk will talk about survival analysis. What's the problem statement? Just kind of introduction to what survival analysis is and why we might care. Um, then we'll talk about maximum likelihood learning, how we define an objective function for learning a model to do survival analysis. We'll then introduce the classic Cox model, which is really, you derive it just from making something called a proportional hazard assumption. I'll talk in detail about what that is. Then we'll start moving into deep learning. Probably the first model that married the two kinds of approaches was something called DeepServe, which is just a deep learning twist on Cox proportional hazards. Then I'll spend a little bit of time just talking about discrete time models, which allow you to break the proportional hazards assumption and really make a flexible deep learning approach to survival analysis. And then hopefully we'll have some time for Q&A at the end.
Let's test.
So let's start with a problem statement for survival analysis. So presumably you're all working with healthcare data. So let's imagine that we have some event that we're interested in some healthcare records. So this event could be disease progression, or it could be a patient's death. And we want to model who will experience this event and when the event is going to occur. There's a problem that comes up in this situation very commonly, and it's that for many patients, we probably won't be able to observe the event that we're interested in. And this is because patients drop out. So maybe they're lost to follow up. You're tracking them for years. And you're trying to see whether they're cancer progressors or something like that. But maybe they just stop replying to the surveys. They move to another country. Or inevitably, your study ends. So you enroll people over a period of 10 years. But today, you're going to finish your study. Some people have not yet had the event of interest yet by the time you finish your study. And you don't know what's going to happen to them in the future. You just don't observe the future. This is called censoring, and it's ubiquitous in healthcare data sets, and particularly, if you're going to work with any historical cohort, training models on the EHR, you're going to come into a censoring problem. Analyzing this kind of data is a central problem with survival analysis. You can think of survival analysis as any kind of method that handles data where there's an event of interest, you care about when that event is happening, but there's censoring. So to make this precise, let's mathematically describe what we're interested in. So let's denote by TI the time between some fixed starting date, which is probably some kind of treatment, and the event that you care about. For example, like cancer progression. So you treat somebody and you want to know after treatment how long does it take for their cancer to progress. And I'm going to index it by I. I will be the ith patient in the cohort. And for convenience, we can always set the treatment time as 0 for that patient. So if TI is 1 year, that means they were cancer-free for 1 year and then they progressed. We also need to model another variable, which is the censoring time. So that's the time when we stop following the patient. So it could be the time when our study ends, or it could be the time when the patient drops out. Now, the important thing to know is that the behavior of this data set is going to change depending on which is bigger. So if the censoring time is greater than the event time, that means we observe the patient long enough to witness the event. We can actually record it because the censoring time was after they had the event. On the other hand, if the censoring time is before the event time, that just means that we don't observe the event at all. So the patient dropped out, or the study ended before they had cancer progression. And all we know is that by the time that the censoring time occurred, they haven't had an event yet. That's all that we know. We can denote whether or not we managed to observe the event by another variable called delta I. And we just say that delta I equals 1 if we observe the event. So delta I is 1 if the censoring time is greater than the event time. And delta I is 0 if the opposite is true. So this is easier to explain with a timeline. So let's imagine this is somebody's timeline. So they have treatment at time 0. then they are cancer-free for a while, and then they progress at some time TI. And then you follow them for another while, and then eventually the study ends or they drop out. So that's the censoring time. So this is an example of a case where we have uncensored data, we observe the event of interest, and CI is greater than TI, and delta I is 1. Here's another example of a different patient. They have treatment again at time 0, but they get censored before their progression. So in this case, you don't actually witness progression. It's happening after they've dropped out. Now, you can visualize this by imagining there's like a gray rectangle after the censoring time. Everything after the censoring time is invisible to you. And in a real data set, you wouldn't see the progression at all. This is just a mathematical construct. In a real data set, obviously, you can't see progression if it happens after censoring. You can only know the progression if it happens before censoring. So in the first example, you observe the progression time, the event time, TI. Remember, it could be anything. It could be death. It could be some other event of interest. And delta I equals 1 because you observed it. In the second example, you only observe the censoring time, and delta I equals 0 because you didn't observe progression. So just to recap, in the ideal world, you have two variables. You have the event time and the censoring time. But in the observational world, you can't see all of these. Instead, what you get is if the event time happens first, then you observe the event time. But if the censoring time happens first, you only observe the censoring time. And you can summarize this by saying that what you observe is another variable called y, and y is just the minimum of the censoring time or the event time. So basically, you only observe the first thing that happens. You will never observe the second thing. And we also observe whether or not it was censoring that happened first. You know whether the person dropped out first or whether the person had the event first, and that's delta. So in summary, in survival observational data, we only observe yi and delta I. And you can think of the key challenge of survival analysis as being, how do we draw conclusions about TI, the event of interest? That's all we really care about. We don't care about censoring. We care about when the event is happening. How do we draw conclusions about TI, given that all we observe is yi and delta I? That's the main question survival analysis is trying to address. So the way we approach this is similar to the way we approach any other kind of probabilistic modeling problem, and that's maximum likelihood learning. And it provides us an objective function to mathematically optimize. So let's talk about the likelihood function. You can view all survival analysis as just ways of running this kind of maximum likelihood procedure. And this is going to apply for classical methods like Cox proportional hazards. And it's also going to apply equally well for modern methods like deep learning. So what is maximum likelihood? Well, first of all, to recap, the likelihood function is the probability of the data given the parameters of your model, and you can write it as P of data given parameters. In our case, the data is going to be this bag of observations, yi delta I, and there's going to be n of them. So I'm denoting this by using the curly braces, and I have a subscript I that runs from 1 to n. I is going to index the patients. And for each patient, you know the yi, which is the minimum of the censoring and the treatment, the censoring and the event time, and you know delta I, which is the indicator function that tells you whether or not you observe the event. And the parameters, this likelihood function, you need to condition on the parameters. The parameters depend on what model we choose to model the data, the probabilistic model. So it could be, depending on the different kind of model we use, whether you use neural networks or not, that is going to change the way that we choose the parameters, and it's going to change how the parameters affect the likelihood. We're going to denote the parameters by theta, because that's common practice in deep learning. And in addition to this, we'll actually also usually have covariates for each patient. And these are indexed, again, by the patient number, xi. And these are things like sex, smoking history, risk factors. They're properties of the patient that are useful for predicting their risk. In that case, the full likelihood function can be written as the probability of the data conditioned on the parameters and also the patient-specific covariates. So in our notation, this is going to look like the probability of the yi's and the delta i's conditional on all of the xi's, so all the patient-specific covariates, the age, the sex, the race category, etc. And at the end, we also always condition on the model parameters theta. And if each patient is independent of every other patient, which we usually assume, then this final likelihood is just a product of the individual likelihoods for each patient. So it's a product of the probability of observing yi and delta I, conditional on the patient's covariance xi, and conditional on your model parameters theta. So now there's two immediate questions once you write down the likelihood. How do we choose the statistical model? So, this choice is going to determine the form of the likelihood function itself. And secondly, once we've chosen the statistical model, how do we choose the parameters theta that we should use with that model? So model selection, that's the first question, is probably the most difficult part. It's going to depend on what assumptions you're willing to make about the data, what assumptions are plausible. It's also going to depend on your computational resources, and to a large extent also will depend on your familiarity as a researcher, what kind of models you're comfortable with using versus what kind of models you don't really want to use. So this is really where a lot of the thinking has to happen. In this talk, we'll discuss three families of models. We're going to discuss the classical model, which is Cox proportional hazards. Then we're going to talk about deep serve. And finally, we're going to talk about discrete time learning, deep learning models. They all are learned with the maximum likelihood principle, but they all specify different ways of the functional form of the likelihood. Thankfully, for each of these models, once you write the likelihood that is specific to that model, you can use the same method for estimating theta for each of them, which is the maximum likelihood method. So, maximum likelihood learning, to recap, you just choose the value of theta that maximizes the likelihood function. So that's really how you choose theta. There's nothing else to it. And now, so far, everything has been totally general. I've said that there is some likelihood function of the observed data given x's. For survival analysis, it turns out that you can write this likelihood in a specific way. I'm going to walk through this. So the likelihood function can be written as a product over all patients. That makes sense. Every patient is independent of two terms. One term is the probability density of having the event at time yi. So yi, remember, is the observed event time. Xi is the patient's covariance, and theta is the model parameters. And this is raised to the power of delta I. So what does that mean? If delta I equals 1, then this is just raised to the power of 1. So you just get the normal factor. And that makes sense. If delta I is 1, that means you've observed the event. So you get a term that corresponds to the event observation at that time. If delta I equals 0, that means you didn't observe the event. If you didn't observe the event, this gets raised to the power of 0, which in other words means that it just disappears from the likelihood. So if you didn't observe the event, obviously, there's no contribution for the probability density of the event at that time. Now, the interesting thing about survival analysis is that you get a second term. The second term is the probability of not having the event before that time. So it's a probability of the patient, quote unquote, surviving until that time. And then it's powered to 1 minus delta I. Think about it again. If delta I equals 0, that means you don't observe the event. That means all that you see is that they survived up to that time. That's all that you know. They survived up to that time, and then they didn't have the event. That's where you get the S function from. And conversely, if delta I equals 1, then this term disappears, and instead you just use the probability of having the event exactly at yi. So you can view each patient as, for each of them, you either observe them surviving up to time yi, or you observe exactly the event at time yi. And I've introduced some notation here. F is the probability density of the event. S is the survival function, and it's defined, as I mentioned earlier, as the probability that the event time is greater than some specified value yi. So it's the probability of not having experienced the event of interest by that time. Now, one thing you'll notice is that in order to write this down, I've had to introduce two different functions, and it's a bit annoying. It turns out that you can rewrite this entire likelihood by introducing one function only, and that is called the hazard function. The hazard function is defined as the probability density of having the event at time t. So you can conditional on not having had the event before that time. So you can see here the way it's defined is t is a random variable of the event, capital T, and you're looking at the probability that happens inside a tiny window from little t to little t plus t plus little t plus delta t, and it's conditional on the fact that capital T is greater than T. So basically, conditional on the fact that you survive up to time little t, what's the probability that you will then have the event within time t plus delta t? That's the hazard function. So the interpretation is the hazard function is the probability density of having the event occur exactly at time t, conditional on not yet having had the event before time t. And the useful thing about the hazard function is that we can rewrite all the terms in the likelihood just using the hazard function. And one of the important pieces of that is the following theorem, which I will not prove. And this theorem states that the hazard function and the survival function, which is that function I introduced earlier, of the probability of not having the event by a certain time, the hazard function and the survival function are related in the following way. If you know the hazard function h, you can integrate it between 0 and t, put a minus sign on it, exponentiate the whole thing, and that's a survival function. So the key point is that knowing the hazard function and knowing the survival function are two sides of the same coin. You can interchange between them just by performing an integration or differentiation. And the proof sketch is you need to write the survival function as a product of conditional survivals. So the idea is that surviving up to time t is like surviving up to time delta t, and then conditional up on delta t, you survive up to time 2 delta t, so on and so forth. And then if you write out that whole product and you take the limit as t equals 0, you get this expression. But it's okay, I'm not going to prove that here. We can just take that for granted. So theorem 1 implies that we can write the likelihood entirely in terms of the hazard function. In other words, once we specify the hazard function, we have specified the entire likelihood and hence specified the entire model. So after some algebra and rearranging, so remember going back a couple of slides, we found that the likelihood was written in terms of F and S. We're now going to rearrange it so that it's written entirely in terms of H, the hazard. And turns out that if you do a few lines of algebra, the same thing can be written, but H is in place of F, and the integral of H is in place of the survival function S. It's usually easier to work in terms of logarithms, which is true in most of deep learning objectives. And so if you take the logarithm of this, the deltas come down and the exponentiation goes away, and you have a sum of log likelihood terms, but it's actually really now a sum of log hazard function terms, and then a term that is an integral of the hazard function. So again, we can reinterpret the terms here. The second term here is the probability of surviving until time yi. So it's integrating the hazard function from 0 to yi. So there's a term that comes from just, not having the event yet. You observe you haven't had the event yet, therefore you get a term. If the patient is censored, then the first term is actually 0 because delta I equals 0. So if the patient is censored, then there is no contribution in the first term. The only contribution to the log likelihood is just the integral of the hazard function, the probability of surviving until time yi. If the patient is not censored, then the first term is you get multiplied by 1. And that's it. That's the probability of having the event at yi, given that they survive up to that point. So again, this is just the exact same structure as the previous equation writing down the likelihood function, except now everything is being rewritten in terms of one function, which is the hazard function. And from now on, the hazard function is going to be our central focus. So far, I have not made any assumptions at all. This is going to be true of any kind of survival analysis whatsoever. But now I'm going to introduce the key assumption that brings us to classical survival analysis, which is the Cox model, and this assumption is called proportional hazards. So the proportional hazards assumption can be written the following way. So we make the assumption, and this assumption, is either going to be justified based on your intuition or scientific background knowledge, or it's justified just for the sake of computational convenience. But in either way, you are forcing this assumption onto the data. And it says that the hazard function, which could in principle be some arbitrary non-negative function, is actually going to be factorized in the following way. It's a product of two terms. The first term is h naught of t, and that's some arbitrary function of time that does not depend on the covariates x. So remember, x are the covariates that are patient-specific. H naught of t does not depend on x, and it's known as the baseline hazard function. The second term is e to the theta transpose x, where x are your covariates, theta is some vector or parameters, and you dot product them, and that exponentiates then you exponentiate the dot product, and then you multiply it by the baseline hazard. So the parameters theta are actually more commonly denoted beta. Like if you use any kind of statistics package, you'll usually refer to this as beta. And these are known as the hazard ratios. And they have a very straightforward interpretation. If theta multiplies some value of x, then that is going to lead to a multiplicative factor in the exponent. This multiplicative factor is going to multiply the baseline hazard function and going to scale the entire hazard function up or down. So if the multiplicative factor is greater than 1, the hazard is going to go greater than 1. The hazard will be scaled up. If it's less than 1, the hazard will be scaled down. And that's where you get the name hazard ratios from, because it's the ratio of the two hazard functions. But notice what happens is that none of this affects the time dependence. The time dependence is either stretched uniformly up or stretched uniformly down. I'm going to make this more graphically precise. So on the top curve here, I've plotted the hazard function, some arbitrary hazard, baseline hazard function h naught of t. So on the x-axis is time, on the y-axis is the baseline hazard function, and this is just some random function. So it's some function that was randomly generated with a computer. Now, remember theorem 1? Theorem 1 states that if you know the hazard function, you can calculate the corresponding survival function by using the exponentiation of the integral. Now you can run this integral numerically on this hazard function h naught, and then if you use theorem 1, you get the following survival function. Now notice a few things about the survival function. If first of all, the survival function is monotone decreasing. In other words, the probability of not experiencing the event can only go down. It can't go up again. Whereas the hazard function can go up and down. And the other thing to notice about the survival function is that when the hazard function is high, the survival function starts to dip. And when the hazard function is low, the survival function will plateau because basically no more events are happening. The hazard is low. So this is the hazard function and the corresponding survival function just for the baseline hazard. This is without introducing any covariates. But in the Cox proportional hazards model, we're going to be multiplying the baseline hazard function by some proportionality terms. And this gives the following kind of graph. So on the top here, I'm showing what happens if you take the hazard function from the previous graph and you multiply it by some term eta, where eta is just e to the theta transpose x. So you can see that if eta is, the more positive or negative eta, sorry, in this case, eta is actually the exponent. It's not e to the exponent. So the more positive or negative eta is, the more you scale up the hazard function or scale it down, but the shape never changes. So notice that the shape is, there's one hump here and it goes down as a second hump. All of the hazard functions are going to have the same overall shape, just scaled up and down. And when you run them all through theorem 1, you're going to get all the following survival curves. And notice that no matter how you scale the hazard function, the survival curves can't cross each other because they're just going up and down with the same shape. So this is the kind of model flexibility you have from the Cox proportional hazards assumption. Yeah, and no matter how we choose theta or x, it's impossible to make the survival curves cross each other under this assumption. So now there's still one problem, which is, given we've made the proportional hazards assumption, how are we going to choose the baseline hazard function, h naught of t, and how are we going to choose the hazard ratios theta? And the answer, as always, is that we're going to use maximum likelihood learning. So remember, we need to find theta to optimize the log likelihood, which is this expression in the hazard function, and this integral of the hazard function. So the first thing we're going to do is we're going to substitute in our assumed expression for the hazard function into the optimization objective. So substitute it in, and there's going to be a few lines of algebra now, which I'm going to skip. If you perform this substitution and you simplify the objective, we find one really interesting property, which is that the likelihood function L, which in principle could depend on the entire shape of the baseline hazard function, it actually only depends on the baseline hazard function at a finite number of time points, which are the observed event times. So think about it this way. The likelihood is a function of the hazard function. The hazard function is some smooth function of time. We plug it into the likelihood, and it turns out we don't need to optimize over all hazard functions. Like in principle, you could imagine you need to run a kind of infinite dimensional optimization over all possible hazard functions. It turns out it only depends on the hazard function evaluated at a few discrete time points, which happen to be the observed time points, which makes sense because the likelihood function, it only sees h at those observed time points. And what you can do is you can maximize the likelihood function analytically by taking partial derivatives with respect to those observed values of the baseline hazard. And you can optimize those out and substitute them back in. So it's just like regular calculus. If you want to do a two-dimensional optimization problem, you just optimize with respect to the first variable and then you substitute it back in. So what we're doing is we're optimizing with respect to the baseline hazard and we substitute it back in. And it turns out this allows us to algebraically, without using any computer software, we can algebraically eliminate the baseline hazard entirely from the likelihood expression, which dramatically simplifies the problem. So the key takeaway is that even though at first glance, the Cox-PH model requires learning the hazard ratios and the baseline hazard function, fortunately, we can algebraically optimize the likelihood over all possible baseline hazard functions and substitute that back into the objective. So in practice, we only need to learn the hazard ratios. We don't actually need to learn the baseline hazard at all, which is, practically speaking, why Cox proportional hazards is so popular, because of this dramatic simplification, which means that we don't actually need to bother learning this flexible hazard baseline hazard function. We only need to care about learning the parameters in the proportionality constant. So once you substitute those optimal baseline hazard function values back into the likelihood, we obtain something called the Cox partial likelihood. And it looks like this. So it's a product over D, where D is no longer the number of patients, D is the number of observed events. So if you have 200 patients, but you only observe 100 events, and the other 100 patients get censored before the event, then you're only going to take a product over D, over 100. I of J is the index of the patient that has the jth observed event. So let's say the first patient to have an event is patient 7. Then that is going to be the first term in the product. You're going to consider the first patient has the event, then you consider the second patient has the event, and so on and so forth. And RJ, which is the set that you sum over in the denominator here, is the jth risk set. The risk set is defined as a set of all patients who have not been censored or had the event by the time of the jth event. And the way to interpret this is that RJ is really the set of all people who could have had the jth event. They're all the people who are still under observation and who haven't had the event yet. So they're the kind of pool of people who are at risk of still having the event. And this exponential term at the top here in the numerator is the relative hazard of the person who actually did have the event at that time. So you can view the partial likelihood as the product of all the normalized relative hazards for the actually observed events. So in the numerator, it's like the hazard ratios of the person who had the event, and the denominator has the hazard ratios of all the people who could have had the event at that time. And then you just take a product over all the events. And this is derived directly from the maximum likelihood principle after you substitute in the values of the optimal baseline hazard function. So we've now simplified the problem dramatically. It turns out that all we need to do is first of all compute the partial likelihood, which is very easy. You just need to substitute the values of x and theta for all the events that you observed. And now we need to optimize it with respect to theta, which is normally called beta. These are the hazard ratios. This turns out to be a convex optimization problem. So it's really easy to solve using an iterative method like Newton-Raphson, and it converges very quickly. And if you use any kind of R or Python stats library and you do Cox proportional hazards, they will be running Newton-Raphson in the background and solving this objective function for theta. So we turn a potentially infinite dimensional optimization problem into a very simple convex optimization problem for theta. So that is all classical proportional hazards. And if you've done any kind of survival analysis before, this is all old news. What I want to talk about now is the kind of developments that started in 2017, where people looked at this model and said, okay, how can we introduce deep learning into survival analysis? And the first method I'm going to talk about is called deep serve. Deep serve is very simple to understand conceptually. It's a Cox pH model where the linear predictor theta transpose x is replaced by a deep neural network. That's all we're doing. So the deep serve assumption is very similar to the Cox pH assumption, except now we assume the hazard function can be written as a product of two terms, where the first term is still some arbitrary baseline hazard function, which doesn't depend on x. And now the second term is still this exponential, but whereas previously we had theta transpose x inside the exponent, now we have f theta of x, where f theta is some deep neural network, and theta denotes the weights of that deep neural network. So we are still maintaining proportional hazards, but we are replacing the linear predictor with a multi-layer neural network. That's all that's happening in deep serve. So the advantage of making this kind of assumption is that because we maintain the proportional hazard assumption, we can do all the same algebra that we did in the previous section about Cox pH, except the only difference is that your objective function is going to have f theta of x wherever it previously had theta transpose x. And so this is very straightforward to define objective function. And we can optimize it using gradient descent, like using Atom or something like that, mini batch gradient descent or something. It's no longer a convex optimization problem because neural networks are not convex. But it's straightforward to write down this objective. And if you have code that already does Cox proportional hazards, it's straightforward to just edit that code a bit, and now you have deep serve. The disadvantage is that you're still going to be maintaining the proportional hazards assumption, and you might have wanted a more flexible model in the first place. That probably why you went beyond Cox pH, but you're still committing yourself to this proportional hazards assumption, even though your neural network, like no matter how big and complicated your neural network is, you're still going to have proportional hazards. Another disadvantage is that whereas Cox pH would converge basically instantly with a few iterations of Newton-Raphson, and because there's only one global minima in the Cox pH partial likelihood, optimization was basically an afterthought in Cox pH. Now optimization is going to be a difficult problem, just like with any deep learning method. You're going to have to tune hyperparameters. You're going to have to tune the learning rate. You might have to regularize. All these things are happening just like in regular deep learning. So now I want to help you visualize, how proportional hazards works in deep serve. It's going to look very similar to Cox pH, except now the rate at which you're scaling the hazard function is no longer linear. So you could have a case where you change x by a little bit, but it jumps a huge amount. So for example, going from the brown curve to the red curve to the purple curve, the scaling is no longer linear in x. But notice that they're all still scaled versions of the baseline hazard function in t. So the time dependence is still uniform. And if you compute the corresponding survival functions using theorem 1 again, you're going to get these survival functions. And notice that even though we have broken the linearity assumption in x, we still have a situation where it's impossible to model survival curves that cross each other. So that's due to the proportionality assumption. And that's true in deep serve, just as it was true in Cox pH. So you can think of deep serve as like the next step up from Cox pH. If that is still not enough to model what you care about, you're going to need more complicated models. And I think the simplest next stage is to move beyond proportional hazards into using a discrete time model. So how does this work? So what you can do is you can take the treatment timeline. Here, treatment is happening at time 0. and you discretize time from time 0 onwards into bins. So yeah, bin 1 is a certain amount of time, bin 2 is a certain amount of time. You can imagine each bin represents like 3 months of time or something like that. And now we need to define a discrete time hazard function. So previously when we were talking about hazard functions, they were all continuous time functions. Now we have the discrete time hazard function, which is just the probability that the event of interest occurs in the kth bin, conditional on the fact that it didn't occur in bins 1 to k minus 1, and conditional on the covariates. So if you remind yourself of the definition of the continuous time hazard function, this is exactly the analogous quantity, but now it is discretized, and in many ways is much easier to work with. So analogously to the continuous case, we can rewrite the likelihood function entirely in terms of these discrete time hazard ratios. So previously we rewrote the whole likelihood function in terms of the continuous time hazard ratio. If you do the math again in the discrete time case, you get the following expression. And you don't have to worry about the contents of this expression. The only important thing is to realize that the full likelihood involves multiplying over all these discrete time hazard functions, and that this is very straightforward to compute on a computer. You can just put this into your Python code or your R code, and you get a number out. So we can easily compute the likelihood, provided we specify each of the hazards, HIK. And remember, HIK is the probability of having the event if your patient I at time bin K, conditional on not having had the event before the kth time bin. So how do we specify that probability? The idea behind deep learning models is that we're going to specify this HIK with a deep neural network. So HIK is some f theta of xi and k, where xi is the patient covariates, k is the time bin index, and you're going to need to have some kind of softmax on the end of f theta, because HIK is a genuine probability. It needs to be between 0 and 1. So again, we can learn theta by maximum likelihood. And this is done using stochastic gradient descent. And this is the idea behind a model called NNet survival, which was proposed in 2018. And there are many models that kind of take this idea and extend it in various directions, either modeling competing risks or anything else like that, or maybe they reparameterize it differently. But the basic idea is the same. You discretize time, you model the probability of having the event in each time, and you do regular neural network gradient descent to find the optimal variable of theta by performing maximum likelihood. So that's the last model I'm going to talk about. And just to give you a sense of what could be possibly learned in this case. So I'm going to show again, on the top is the hazard function, the bottom is the bottom is the survival function. But now you no longer have the proportional hazards assumption, and time is discretized. So notice how there's all these little dots here. That's because I'm showing a discretized version. And the curves, the hazard curves, are no longer proportional to each other because we are not making that assumption at all. So we can't do that trick where we analytically optimize out the baseline hazard function. We are now having to learn the value of the hazard function at every time bin. And because they are no longer proportional, you can see that the survival curves implied by the hazard functions can now cross each other. So if you look at the red circle, the blue and the orange survival curves, so these are survival curves for different patients, they can actually cross. And this is something that was impossible to do with DeepSurf or with Cox-PH. So if you think that your data, is well modeled by a situation where survival curves for different patients can cross each other, then you are going to need to do something beyond DeepSurf and beyond Cox-PH. And this kind of discrete time neural network model is a very good approach. So yeah, that's my last slide. We've talked about 3 models now. We talked about Cox-PH, DeepSurf, and NN survival. There's many, many, many more in the deep learning survival analysis literature, but if you understand these 3, you'll have a good base for which to read any other paper in the literature. So that's it. That's all I have for today, and happy to take any questions. Thanks.
Wonderful. We're excited to open it up for some questions. You can either post them in the chat or just come off mute. But what is it? Any questions from the audience?
Yeah, I've got a question.
Yep, go ahead.
Thanks so much, Andrew. This is really informative. I just wanted to ask, like, how well do you see these methods and approximations actually translate into real practice? Because obviously there's quite some big assumptions that we make, and I just wonder, actually in practice, how well do these then work in reality?
Yeah, so I think it depends on kind of data you have. So one thing that's becoming very, very popular is survival analysis in the presence of high-dimensional input data. So imagine you have pathology scans that go in, or CT scans that go in. You can imagine that doing the Cox proportional hazards assumption is completely ridiculous. So if you go back to Cox PH, the Cox PH assumption, if X is an image, then theta transpose X is a linear feature. It's an utterly ridiculous assumption. So the moment you have high-dimensional covariates, Cox PH is terrible. And you want to at least do something like deep surf, where you could have, when you go back to deep surf, you could have F theta could be some like CT foundation model or pathology foundation model. So I think the covariates immediately force you to make a decision there. The other bigger decision after that is whether or not you can still make proportional hazards. I think that is a harder decision to make, and it really depends on intuition that you have about how the features affect survival, and whether or not you have these really nonlinear effects where certain features can force somebody to have a really terrible risk, whereas other features don't. I'm less sure about that. So I think I won't comment on that. I think probably other people would know better than me how accurate that assumption is for their methods. But I would say for sure, if you have high dimensional covariates, then it is necessary to make this kind of more general assumption, and that's at least very useful.
Yeah, cool, interesting. And I guess so what we've been doing is we kind of just start with the Cox model as simple as possible with as low dimensional problem, and then we just kind of keep scaling it up. I guess would you in a toolkit, is that the way you'd approach it, or
I'd say
have
if
any
you
other
only
advice about what to do?
If you only have tabular data, then Cox PH is a great way to start. But I'd say the moment you have things like X is like foundation model embeddings, then like Cox PH just stops making any sense. Like a very common pattern is like you have pathology slides, you embed them into a 1,000 dimensional embedding vector. I really don't think you want to do Cox PH anymore, but it's the baseline to beat. You always have to do the dumb baseline first. So if you're doing any kind of deep learning survival, you must always compare it with Cox PH. And if you're not beating Cox PH, then something has gone wrong, or maybe your deep learning model is unnecessarily complicated and you can throw it away. But yeah, I think what you're saying makes a lot of sense. Always start with the simple thing.
Cool. Amazing. Thanks. And then just as a quick question, final one, where would you, because I was familiar with both of these methods and the discrete time survival, what comes next? Like, because I wasn't aware that there was other ones. Do you have a pointer?
So I think there's a bit of literature here, but maybe the other thing to think about that would add another layer of complexity is competing risks. So in many data sets, you would have you might be interested in something like cancer recurrence, but you'd have death as a competing risk. And if the patient dies, it's possible for them to recur. The correct way to model this is with a competing risk model, and you should not treat in the correct probability theory, you should not treat death as a form of censoring. You have to model it explicitly. And what you can do is you can write down hazard models that have two heads for the hazards, or you might have many different outcomes, and you have multiple hazard heads. You basically take the same ideas here and you add like many more dimensions to them. There are other like research areas where you basically that amount, in my opinion, to just parameterizing things differently. So we parameterize things with the hazard. There's also models that parameterize things with the cumulative incidence function and things like that. But the math in the end is just a transformation. So I don't think it's a very big difference, but people have found different levels of success with different parameterizations. So on a practical level, it's important.
Yeah, I guess you could use like splines to model the hazard function eventually.
I'm sorry?
Yeah. I was just thinking rather than like modeling it as discrete probability time bins, I guess you could model that as like a spline or actually as a continuous function in
Yeah,
a
sorry,
kind
did you
of
say spline? You cut out.
spline, like a like a mathematical spline where you like
Yeah,
draw
yeah.
in like,
Yeah, I could totally imagine that could work. Like in the end, all these are all like function
mm,
approximators, and
mm,
neural networks are function approximator, linear functions are function
mm,
approximators, splines are function approximators, Gaussian processes are functional approximators.
yeah,
Like there's so many options to choose from, and it really depends on what's flexible enough, but is still, something that's easy to
yeah,
use.
constrained to your data. Cool, amazing.
Yeah,
Thanks so much.
yeah, no problem.
And Till?
Yeah, thanks from my side as well. This might not be directly related, but it's something I've been thinking about, and I'd be wondering how that fits in here or what your thoughts are. Say you have a situation where you have different groups, where you're not estimating comparative, let's say, loading of different covariates on the longitudinal development, but let's say you have different groups that show, let's say, different temporal patterns in some variable. For example, you also showed nonlinear functions. And let's say you have two groups where one group has one type of nonlinear function, another group has another type of nonlinear function. What, in your estimation, might be the best method, like that is as simple as possible, but no simpler, to do a sort of temporal PCA? So to estimate which group shows which pattern. Like you could just repeat these methods and do that within groups. That's one option. But I'd be wondering if there's another approach that you know about.
So are you primarily trying to do clustering of the groups, or are you trying to make predictions? Like, what is the end goal of the PCA?
Yes, so imagine this is like to make it concrete. Something I've been thinking about are the side effects of antipsychotics, which are often like metabolic side effects. And one idea that I might be interested in is, for example, prolactin levels between men and women. They tend to show different like temporal patterns of response and adverse events. There tends to be a different onset, for example, between men and women, given baseline differences in hormones. And what I've been wondering is, would it be possible to use one method to estimate different, let's say, temporal patterns, not an event, not a yes/no type of situation, but different temporal patterns over time between these groups?
Yeah,
Does that make sense?
yeah, that makes perfect sense. I would suggest, so if you think the two groups are have very different behaviors, I would suggest going to this kind of discrete time model. Because for example, if the two groups are sufficiently different, you could imagine that it's plausible to assume that it's possible for their survival curves, the average survival curves, to cross. And if it's plausible that their average survival curves cross, you have no choice. You can't use Cox PH, you can't use deep serve. You have to use this kind of discrete time method. And this discrete time method is really flexible. So if you make H an extremely flexible neural network, one of the covariates X could be, sex, and then you can really model any kind of function H. And in order to show the difference between two groups, like one thing you could do is you could, for each member of the group, based on their covariates, let's say you have a test set or something. I'm not really sure how you did, but I'd say based on their covariates, you could predict the predicted survival function for that member of the group. And then you could consider taking the men in one bucket and the women in another bucket and showing that, the model predicts qualitatively different survival curves for men and for women on average. That's one thing you could do, because then it serves the purpose of clustering, because you can see the two survival curves separate from each other. And it also shows temporal information, because maybe each survival curve has like extremely different shape, but the model would still be able to, show you how the shapes are different. So I think if you have enough data, I would pursue a very deep learning heavy approach with a very flexible estimator, and it would be this kind of discrete model.
Okay, and then basically repeat that within the groups.
I would say so. I think for learning the model, I would definitely go with this kind of model. But for displaying the data and showing how they separate, I think there's a lot of options that you have. And maybe the simplest thing I can think of is like just overlaying the two survival curves on average and showing that they are very different shapes.
Yes.
But yeah, there's probably a lot of other ways to do it, and I'm not super sure, but yeah, hope that helps.
All right. Thanks.
So I had a question, especially with your experience with the real world data, Dr. Fong, like, the PSA control tower and other, projects using like the EHR based data. The data can be like really messy, really missing, really patients have different features, don't have different features. So like, especially when it comes to having an index date that starts your survival timeline, like how do you consider that, especially when there's like maybe conflicting sources of information for what the index date might be, or when there's missing data for the index date, or it's like uncertainty within the start of their time in the population?
Yeah, that's a difficult problem. Like the approach we've taken is that you use LLMs to read the longitudinal record history of a patient, and summarize all the records and then try to reconstruct the timeline based on all those summaries. So hopefully with context of the entire patient record, there's a better chance of like getting a good approximate treatment date. We have not investigated ways of handling uncertainty. So if a patient is really uncertain about their treatment start date, we usually try to drop them. But you can imagine that there's ways of training models where you measure the uncertainty in the start date, and then that uncertainty propagates through the prediction. But we've not looked into that. My sense is that unless you have enormous uncertainty in the majority of your patients, that kind of approach is probably going to be complicated enough to not be particularly worth it, and more of the time should be spent on refining the LLM pipeline to make sure that it's as accurately as possible understanding the patient history. So yeah, it's a difficult problem, but our approach is just try to make sure you get that LLM extraction as accurately as possible and review it again and again and improve it all the time.
Your questions from the audience? Probably have time for about one more question. So, any other questions? I think the final one I would say is like, is there one publication or one researcher that you would recommend people check out that they might not have heard of that you think is doing cool work in this space or in the oncology space?
Yeah, that is a great question. I have to say I'm not familiar enough with like the state of the whole literature space to know that. Yeah, I think yeah, I think I'll refrain from give recommendation because I'm not I don't think I've been in this space long enough to kind of know who are the leaders and who's likely to give you good research in the future. I'll just simply say that every deep learning model these days in healthcare, at the bottom of it, there's a very high chance there's a survival analysis happening in the background, and you should just make sure you're aware for each technique what kind of method they're using, what kind of assumptions they're using, and why. Yeah.
Great. Yeah, well, thank you so much, everybody, for joining our session today. We're really excited to get to offer the session and have Dr. Fong here to share all the insights and knowledge that we've had today. So if you have any colleagues that weren't able to join, just email us and we can help you get the recording. And thank you so much for everybody attending today. And thank you, Dr. Fong, for presenting.